We're going to start a bit early as people sort of digitally file in so that we can cover all logistics. First off, we'd like to thank you for joining our final session of the spring semester of this aviation data science seminar series. We obviously appreciate your patience and understanding as we've navigated through these pretty unprecedented and challenging times. So we really do appreciate your tuning in to listen and watch our speakers. Before we begin, we'd definitely like to give a great thanks to everyone involved in putting together this seminar this semester. First off, thank you to NASA and NASA Academic Mission Services, to UC Berkeley, to the UAM at Berkeley team, Berkeley Institute of Data Science, and the Institute of Transportation Studies. And in particular, we'd like to thank a select few folks, specifically Dr. Rajasen Gupta, Dr. David Bell, Dr. Gano Chatterjee, Dr. Banavar Sridhar, and Dr. Mark Hansen, as well as Raj Pai, Saba Hussain, Marcia Fenner, and Amanda Cairo, as well as the USRA and Berkeley organizing teams. With that, I'll hand it over to Sam Fernandez, who will give a brief overview to the students of this class about their end of semester assignment. And then Sam will hand it back to me, and I will give it over to Raja to introduce our speaker for today. Go ahead, Sam.
Thanks, Pawan. Can you hear me now, Pawan?
Yeah.
Can you hear me?
Yeah, we're good.
Okay, great. Hey, so to all the students enrolled, thank you all for bearing with us while we figured out the logistics for the assignment. So we just are asking for a one-page write-up on what you've learned from any four of the seminars. The recordings are available. Just a one-page write-up on key ideas you've learned about aviation data science. And if you can hand that in through B courses, I've created an assignment there that would be wonderful. If you have any issues, please email me and we'll do our best to help you in these difficult moments. Thanks a lot. I'll hand back to Pawan.
Thanks, Sam. Sam will mention that again for the students who may have been filing in later. So we'll mention the assignment again at the end. Just a reminder to everyone to please mute your mics and remove the video so that we can ensure just a clear communication channel. And the final thing, as before, to leave questions in the chat so that our speaker can address them at the end of the chat in case they aren't addressed in the talk itself. So to introduce our final speaker of the spring semester, I'm going to hand it over to Professor Rajasen Gupta.
Hi, everybody, and thank you once again for being on the seminar. As I think you've probably guessed by now, shelter in place doesn't work very well for me. The error that I made and my appearance would have been quite unthinkable in, had we been in normal operation. I want to thank Pawan and Sam to start with for, very comprehensively acknowledging everybody in the seminar. I'd like to, make a special mention of David Bell, who has been my friend, my partner, and my colleague in making this seminar happen. With that, and without further ado, let me introduce Vishwanath Bulusu. It gives me, really great pleasure to make this introduction. Vishwanath got his Ph.D. at UC Berkeley, and I was honored to be his advisor. And I would say after graduation, he has also become a personal friend. He is, a very interesting person, including serving as, I believe, the head of programming or production at the UC Berkeley radio station, a position that he still continues. I think he's one of the, upcoming researchers in this field. And I hope that with NASA Academic Mission Services and Crown Consulting, he will go on to many successes. He has already distinguished himself. And maybe I'll just give one personal anecdote, about Vish, which I laugh about now, but I didn't before, that every time, there were times in his PhD at least twice when I catch hold of him and berate him for working on the wrong problem. I say, Vish, you are working on completely the wrong problem. You have to take my name off this paper. I disapprove thoroughly. And then the guy promptly goes ahead and gets a best paper award from the community. And I'm there saying, oh, you should add my name to your paper. But of course, it's too late at that point. So over time, I have learned to, trust a lot of Vish's intuition. And he's really a very good researcher and a wonderful human being. With that, let's welcome Vishwanath Bulusu.
Thank you, Raja. Wow, that was heavy. Good morning, everyone. Hope you all are well and safe, sitting at home. Thanks for joining the call. Let's get started. If you have a question while we go through, just a request that please add it to the chat box and we'll address them at the end. This being the last seminar, my goal today is to give you an overview of the challenges and opportunities for data science in urban air mobility. So you leave this end of the seminar with some avenues to explore in future in the field. Okay, I'll start by framing the conventional aviation system in the data science paradigm. That should lead us into understanding the challenges for urban air mobility. Then I'll give you 6 examples from my research to suggest ideas for ways to address these challenges. And then we'll end by identifying opportunities for research in the field. Okay, I think of any transportation as a combination of mode, node, and medium. Mode is that which transports. Node is the from and to points. So think of it like origin and destination points or hubs. Medium is that through which the transportation happens. So in that sense, aviation is a combination of aircraft, airports, and airspace. Of course, another part here is aviation, but it's kind of has a little bit in each of these 3 components. So I didn't put it as a separate one, but even that is kind of included. Data science is mainly about extracting knowledge from data. That function comprises of these 5 stages of the life cycle. You capture the data, so you have sensors and things which give you data feeds. Once you have the data, now you have to put it in a structure so you can maintain it and, of course, draw things from it. Just request, I guess, someone's microphone is on. Oh, anyway. So you maintain the data, you put it in a database, and then of course then you can classify and cluster it so that you can now answer questions that you're really interested in, which leads you to the big hero of data science, analysis, which gets a major portion of the limelight. And then once you have analyzed the problem and you have something to convey, then there is a whole field of science on how to communicate those ideas and those results. So now let's think of aviation in the data science lifecycle paradigm. For aircraft, you collect data from sensors all across the aircraft. There are other data links which keep a log of all the data that's coming in. You maintain that data through logbooks on board or through flight recorders. On ground also, you maintain it in server farms. Then you process that to kind of generate these maintenance reports and inspection reports, for example. Once you have all that, you can run analysis. Oh, how is the aircraft performing in terms of its fuel? Well, how is the flight performance characteristics changing over the lifespan of the aircraft? How is the health of the structure? And where are the stresses happening? You can analyze the fleet. If you're an airline, you'd like to know which aircraft can be flown for what leg of a journey and things like that. Once you get all this analysis done, then you can, of course, communicate that into fleet management decisions or NTSB reports, which are generated every year, revenue management decisions and things like that. Again, similarly with airports, airports are another big hub of data feeds, data coming from all the passengers moving through the airport, baggage moving through the airport, the parking lots. So the airports kind of connect ground and air side. So there is all that transition data which comes in. Then of course you maintain them by archiving it into logs and running operation logs for different components of an airport. You process that data to kind of generate these operational reports which help your planning decisions. So how to increase the capacity of the airport, how to address the noise issues, where to put the amenities in the airport, for example. And of course, you communicate this through, a nice example is displays, how to display information for passengers in an airport. Airspace, this is kind of our niche. So me, in my research and at NASA, this is what we primarily focus on, the airspace side of it. Of course, NASA does airport a little bit and aircraft, part of it, of course, a lot of it. But airspace is what you've heard through this semester mostly. So for example, the data capture, maintenance, and processing part primarily was addressed in Ganu's talk last week. So I suggest you go back and check that out if you want a more detailed version of that. Mark in his talk talked about some of the processing and analysis step, which is trajectory modeling and detecting anomalies in trajectories and things like that. Banavar addressed a lot of the analysis and communication part, where he talked about machine learning techniques as applied to air traffic management problems. So this is the conventional aviation. Conventional aviation has had a history of almost 50 years of collecting data, way before any other transportation started it. Today, over the past decade, with the smartphones, the road transportation has picked up in terms of the volumes of data. We still keep phones in, airplane mode on the aircraft, so that industry hasn't jumped much onto the en route traffic. But still, there is a lot of data coming in which is new to the field, and the field itself, conventional aviation, has a ton of data in it. Now, let us look at what urban air mobility adds to this. So urban air mobility, or UAM for short, is about moving passengers and cargo across metropolitan regions by air. So conventional aviation moves it across cities in terms of scale. Urban air mobility is about moving at a smaller geographical region. But here is what that means for future in terms of scale. This is a picture I took of Bay Area, in the Bay Area from about some 5,000 feet. You see more ships in the water here than aircraft in the sky. This is today's airspace, where aircraft are, even in terminal airspace, are supposed to be separated by 3 nautical miles at least. What UAM entails is, if we look at one small portion of the airspace, let's say over the downtown San Francisco area, in future, it will have tens of aircraft, if not hundreds, over the day, meaning there is expected to be almost an order, in quite a few orders of magnitude increase in the density, which leads us to kind of ask the question of how do we scale a system up, right? Let's look back at the UAM system in the 3-component perspective. We have new kinds of aircraft. So we have small under 55-pound drones, primarily electric propulsion. We have the bigger ones which can carry people and cargo to longer distances, eVTOLs as they're called for short. And of course, a new type of airport, vertiports, kind of, you can think of it as an evolution of heliports, to say the least. And of course, a much more complex airspace with a lot of controlled airspace, additional temporary restrictions and things like that, right? So you have all these little chunks of airspace coming together. Which all of this basically means that there are a ton of challenges in the field. And to understand them, let's frame the urban air mobility space also in the data science lifecycle paradigm, and see what is lacking. For aircraft, there are very few small drones which fly, and very few small drones operations which are happening. Of course, people have flown a lot of drones, but not all of that data is available publicly. The eVTOL, the bigger counterpart or the big brother, is still not out there, so there isn't much data on that. Which means pretty much everything else, even though we might have some methods to try them, we can't really do without that data. Airports are a little further behind, being vertiports, because there are conceptual designs. There are some helipads operating. So Uber operates, for example, Uber Copter in Manhattan, but very, very little data, right? And pretty much not really any vertiports as proposed. Again, that whole chunk is pretty much empty after that. Airspace has done some more progress in research over the past 5 years. So NASA started the UTM program. They ran some flight tests over the 4 years. And of course, there's all that data. Then there was some human in the loop simulations and stuff like that. So there is that data stored in databases. There's a Sherlock data warehouse on base. You cluster the simulated data, and you can generate some trajectory models. And then you can analyze things like, can we use existing helicopter routes for operating air taxis in a city or things like that? What are the kinds of separation assurances that you need? Minor analysis that has happened over the past 2 to 3 years. And of course, in terms of communication, there are only basically market studies and reports of predictions. There are some human in the loop evaluations which are also available. But for the most part, clearly there is an overall dearth of data, which is a big challenge because we have to address several problems for this to become a reality. And some of those problems are, kind of the field is nascent for innovation, right? So some of those problems are these. On aircraft, you want to know what is the optimal size of the aircraft that you want to fly. What kind of propulsion do you need? Well, what do you need to provide comfort for these high-speed movement in the air, which also means a lot of acceleration and deceleration? What is the noise impact in the community, and which means how do you design the rotors of the aircraft? What is the flight profile and things like that? Airport, where do you put the vertiports? How many people need to use them? They are connecting the ground and air side. Ground is road traffic, air side, and then the demand will vary because of road traffic. So how do you manage the delays? How do you reduce the transfer time, which is a big component for anyone to convince them to take an alternate mode, right? Airspace is the kind of problems we look at, like what's the number of aircraft we can accommodate, what's the optimal flight planning and routing method and things like that. How do you lay a network in the sky so that you can manage the traffic well? Do you go, let's say I have some 20, 30 vertiports in the region, do you connect them by direct point-to-point networks, or do you follow a more trunk and artery structure like the highways on the road? What are the trade-offs? Where should you put them so that in terms of emergency, these aircraft can land at the best places possible and keep flying safe? And of course, the other kinds of air traffic management decision making. So in short, a lot of problems, not much data, so not a great place to be, but well, here's a ray of hope. UAM is air transportation in spirit, as I like to call it, or in operation, because it's going to operate through the air. But it has some essence of road transportation in terms of scale, because you're moving the demand in a city, which is primarily handled by road transportation. So in terms of numbers, it is kind of like road transportation, which means we can leverage ideas from both the fields, in addition to, of course, innovating methods for other kinds of problem solving. So now we move to the second part of this presentation, where I'll give you 6 examples from our research over the past few years to explain this, kind of a synergy further. The first problem we kind of latched on to about 3 years ago was what density of this new traffic can be handled before the airspace breaks down. Of course, there was no data for low altitude airspace, except that we found there are about 50 to 100 general aviation flights per day in an area like Bay Area. Then we looked at the package delivery industry and we did some back of the envelope calculations and estimated that at maturity, if the market's promise came to fruition, about 100,000 trips per day are possible to be generated just by the package delivery industry. We said, let's visualize what this shift in density entails. So we simulated kind of over the Bay Area, about 100 flights a day to about 100,000 flights a day. These are all low altitude, small drones. Everyone flies direct routes. We just removed all restrictions and said, okay, let's see what happens if that is allowed. Every time 2 aircraft were in conflict, we colored them red, and everything else, every other aircraft is like a green arrow. And this is what resulted. So this is a perspective view of the Bay Area, and all that sea of red that you see is basically on top of San Francisco. You see a lot of sea of red here on top of the Alameda County and Oakland cities like that. And the reason a lot of that is happening is these 100,000 trips, we don't know where they'll start and begin, so we decided to distribute them based on population density. So that's one data set that we have used for this study, right? Then we cluster these data points into, conflict clusters, which I'll explain next. And then we can analyze how to address capacity problems. So let's process that data. We processed that data, and we did that by abstracting the airspace as a graph. So if you look at a snapshot of the airspace, every aircraft is a vertex, and every 2 aircraft in conflict are connected by an edge. The components that form from this are hence the aircraft clusters that need to be jointly deconflicted, and their size is the size of the deconfliction problem. Now, deconfliction algorithms typically degrade, especially in terms of computation time, as the number of vehicles in the conflict becomes larger. So we said, oh, okay, let's see what is the chance that we'll see a 4 or more vehicle multi-conflict happening as we increase the density. and see how that probability of, the system having large conflicts evolves with density. So this is just a summary of what I just told you. And here is the kind of graph that you get. So on the x-axis, I'm plotting the traffic density varying from about 100 aircraft to 100,000. I think we varied it to about 200,000. And we are plotting the probability of observing a cluster of size 4 or more, or meaning a large multi-vehicle conflict. And of course, you see a jump where it goes from very low probability to very high over a certain traffic density. If I look at that threshold behavior in that region, that gives me a rough idea of where the capacity might lie just based on this one metric. And of course, this is for one given conflict distance, where I'm saying 2 aircraft are in conflict and converging and within 1,000 feet, which is what is today's lateral separation requirement, right? Then I can repeat this for closer and closer proximity, saying, oh, 500 feet is allowed, 100 feet is allowed. And if I do that, so there are, let's say 20 cases of conflict distances, 100K or some 100 cases of traffic densities, I can get a 3D surface plot of the probability, which then gives me a plot like this. If I look at from the top, where all the blue is the safe region, meaning that, pretty much the chance is 0. And all the yellow is the unsafe region, meaning this chance of observing a large cluster is pretty much 100%. And so you don't want to operate in this region, definitely not. You definitely want to operate in that region. And this transition zone in between is where you can think of strategies to kind of shift this blue further down. Of course, now we have one hammer, so we can hit a lot of other nails. So we can try the same threshold idea on different metrics. One of the things which we explored further was noise in the airspace from aircraft operating. So we took the same data, same aircraft flying based on population density. The other data source that we leveraged was, there are two. There is experimental data, which is a funny experiment actually. Don't tell, well, I'm telling you now, but basically we were on Berkeley campus. We took one of these hexacopter drones and we just flew it up, and we had our smartphone and another sound meter and basically measured what sound decibel levels we get as this thing goes up to 100 feet, 200 feet, 300 feet, and so on. And we found that about 400 feet, we get a 55 decibel noise or sound. So we said, okay, this is our source noise. And you can think of the sound that you will hear as a drone like that passes over you as a dog, kind of like a fire truck passing by. As it comes closer, which is what I'm plotting on the graph on the right, the orange line, it comes closer, then goes away. The sound goes higher, then falls down. And this is just comparison with a few other models in the field. Then to understand this propagation, we used some of the mathematical models simplified from what is called aviation environmental design tool, AEDT, which is used in conventional aviation to understand the noise impact of conventional aircraft. We borrowed the model from that. And then we said, with all the traffic simulated, let's see what happens as the intensities overlap. You can generate things like this. This is a noise map of the Bay Area, basically the same traffic that you saw earlier in that video. At every pixel, we are adding the intensities from all the flights that are airborne at that time. And you get maps like this, which is basically the average decibel level over the day. This tells you where the concentration happens, but at the same time, it doesn't tell you much about how loud, because it's saying 45 decibels. But that's just the average. To understand what noise is really happening over that portion, we can look at any pixel and look at the time distribution of the sound levels. So we look at the brightest spot, and that's what we plot on the right. And here you can compute another metric called Ln, where n could be any number like 10, anywhere between 0 to 100. What it means is, if I choose L10, I'm saying what is the decibel level that is exceeded 10% of the time. So for this pixel, that was about 53 dB or something like that. So this is another example where we really had no data in the field. We simulated all our data, so synthetic data in that sense. But then we said, oh, let's make it a little more realistic. So here is the next example. In this, we got actual aviation data. Now we're looking at the bigger aircraft, the air taxis, and a lot of these air taxi operations will happen close to airports in metropolitan regions. So the question that we asked was, conventional aircraft has a system called TCAS, Traffic Collision Avoidance System, which is basically your last layer of defense to prevent any mid-air collisions, other than, of course, the pilot. The system issues traffic or resolution advisories based on the time to enter a protected volume around the aircraft, which is the, this region here. Well, the region is actually a little smaller here. This is the RA region. The design is a trade-off between providing necessary separation and unnecessary alerts, right? So therefore, it operates at different sensitivity levels based on the aircraft's current altitude, MSL altitude. The text is important. What I wanted to focus on this figure is the colored regions. The protected region around an aircraft is called DMOD, or distance modulated distance. Tau mod is the time to enter DMOD. Tau vertical is the time for the two aircraft to come to the same altitude. And Z threshold is the current vertical separation of the aircraft. Now, TCAS issues alerts based on limits on those taus. So if you're far away, so 45 seconds or something apart, let's say at 5,000 feet, then it would issue saying, oh, there's traffic on this side, traffic on this side. If it's closer than, let's say, 25 seconds for that same sensitivity level, it will say, okay, now you really need to move, so climb or descend, it will give you an advisory. I suggest, people can actually hear this if you watch the movie Sully, where he's trying to land in the Hudson and TCAS starts saying terrain, terrain, and you can actually hear that. It's a very nice example for people to check it out. But all this data now is from the aviation side. So this is real, we got real track data, and we have the TCAS system as FAA implements it. What about UAM? How do we generate the UAM traffic? There are no UAM flying. So to do that, we looked at helicopter routes in the region. This is a sectional chart produced by FAA of the Dallas-Fort Worth Metroplex region. These are some of the big cities in the area. These are the airports serving the region. We are looking at operations in and out of DFW, primary landing and takeoff. So these are the two main runways. There are 4 runways along this direction, basically. So aircraft either operate coming towards south, so south flow, they come from the north, take off to the south, or the opposite, they come from the south and take off to the north. The UAM, we expect them to operate, we designed those routes, around these helicopter routes, which is what you see in yellow. The helicopter routes basically give you a way for doing what's called visual flight rule operations within controlled airspace. I think internet just got stuck. Can people hear me?
Yes, we can still hear you.
Okay, great. So yeah, so these helicopter routes provide visual references for pilots. We want to explore whether these existing routes, which are approved for the helicopters, right, can be utilized by UAM traffic. Now, UAM flying on these helicopter routes could trigger RAs when they are near these regions, right? And also the 3 conditions have to be met. So remember, I'll try to bring it back again, but the conditions are for the TCAS system to produce an RA, the tau mod, which is time to enter protected volume, should be less than the threshold. And one of either the next 2 should be true, meaning either the tau vertical, which is time to co-altitude, should be less than a threshold, or the aircraft should currently be within 600 feet of each other vertically. And of course, there's an additional added thing in TCAS system, which says that once a conventional aircraft is below 1,000 feet AGL, the system just shuts off, even if it's unsafe. And that's basically to take care of landing on near airports, because there are a lot of aircraft on the ground. And if it doesn't shut off, the pilot will keep getting saying, oh, there are too many aircraft, climb, and he really wants to land. So there's this trick, but basically those 2 conditions, tau mod less than threshold, tau vertical less than threshold, and current separation less than 600. Here are the 2 regions where the prime issue happens, because UAM are crossing the path of the aircraft taking off and landing. On the north, we didn't have much of a problem. There were really no RAs issued, there were no alerts. But on the south, something interesting happened. And let me walk you through an encounter graph to kind of explain what's happening. On the x-axis, I'm plotting the evolution of the encounter time. On the left y-axis, I'm plotting the vertical separation of the aircraft as they fly, again, in the air. So the dotted blue line here is the threshold. The solid blue line is the evolution over time of the vertical separation. On the right side, I am plotting the 2 taus, tau vertical and tau mod, right? The threshold is between 0 to 15 seconds. The solid line is tau mod. The dotted line is tau vertical. Now, for an array to be issued, the tau mod for this encounter, this is at South Crossing, this encounter, the tau mod is less than 15 seconds during this portion of the encounter. Tau vertical is less than 15 seconds during this portion of the encounter. They don't overlap, so one condition is not satisfied. Great. Let's look at the next one. Well, the aircraft are closer than 600 feet vertically after this time, meaning there is this region here where it should trigger an RA because they are happening at the same time. Except something interesting happens. Just before that region starts, the conventional aircraft is already below 1,000 feet AGL, so the system shuts off. It doesn't produce any RAs. So in that sense, great, this doesn't produce an RA, right? But that separation of producing and not producing an RA turns out to be just about 7 to 10 feet, which is nothing. I mean, the big aircraft have errors bigger than that. The small UAM, we are asking them to be really precise about their trajectories. So in that sense, it's not really safe. So the next thing we did is we added uncertainty to the UAM flight data. So we added uncertainty to the altitude. We said, let's take the mean altitude and add some normally distributed error with zero mean and different standard deviations. And we ran simulations with that. Then we said, oh, if we lower the altitude, so we changing mean by -5 and then -10. So lowering the altitude, adding standard deviations, normally distributed errors. And then we said, let's see what's the chance of triggering an array. Here is an example. So this on the x-axis, I'm plotting the time from noon to about 3 p.m. in the DFW region. The y-axis is the chance of triggering an array, and each colored graph is basically different standard deviations. And each one figure is one mean altitude. So here I'm keeping the altitude unchanged. Here I'm bringing it down, the whole thing down by 5 feet. Here I'm bringing the whole thing down by 10 feet. And what we observe, to summarize, is that as we do that, the chance of triggering an array goes to under 10% if we lower the mean altitude by about 10 feet. But again, this is still very close, but not that much of an effect. What this ended up in resulting is that the team that was designing the routes, of course, they got input from subject matter experts too. And the south routes were kind of redesigned and pushed further away from the runway to kind of create that separation. This and the previous two examples are interesting in the sense that the first two examples, we just produced data, we simulated data. We got some non-traditional sources, so population density. Here we got some real aviation data from the aircraft tracks. We got TCAS. We also used some simulated data for the UAM. The next example was a natural evolution where basically you can think of it as these two systems on steroids. So a couple years ago, or actually a year and a half ago now, we asked this question of, hey, we want to operate in the cities. There are so many different kinds of airspace constructs. How do we find at different altitudes what airspace is actually free for me to even operate? So we call it airspace availability. Kind of a global effort. So it was me here, Parker in MIT, Valentin in Sweden, and another student, Jungwoo, in Korea. So of course, we all had our own ideas on what should be included. We ended up including 7 airspace constructs, right? So one, of course, is the terrain and obstacles. So we got that data from public terrain and parcel databases. Then there is controlled airspace, class B, C, D, and all that around airports, which we got from FAA's 28-day NAS resource. Then, the small UAS part 107 rulemaking, and part of that, there were these facility maps which are created for operations in the low altitude. So we got those facility maps from FAA's OpenArcGIS database. Then there are airport approach and departure procedures, which is basically like a cone which starts from the runway or ends at a runway and kind of goes out like a volume, and an aircraft landing or taking off is within that cone. So we got that from the FAA's Coded Instrument Flight Procedures, CIFP for short. Special use airspace, these are temporary restrictions. For example, if a game is happening at a baseball park or Oakland Arena or something, then there's a cylinder of airspace restricted and you can't fly over it. We got that from notice to airmen in a region which have that data. Then there are these things called minimum vectoring altitudes, which basically says that anywhere in a geographical region, there is, about every point, there's a minimum altitude below which the aircraft shouldn't go. The aircraft might, so for example, on top of Berkeley, let's say it's about, 5,000 feet. So no conventional aircraft, general aviation, if in emergency maybe, but conventional aircraft won't come below that minimum vectoring altitude. especially in terminal airspace, unless there is an emergency. So for that, that construct we got from the Aeronautical Information Services. There are a few special flight rule areas in the country, which is basically VFR corridors kind of thing within controlled airspace. So there is one in LA, there is one in the Hudson Valley. So we got these, as you can see, 7 different data sources to get all these constructs. I'll come to the scenarios in a bit. We get these constructs as 3D polygons, and then we slice them and at each altitude level. So we get a 2D polygon, which is what you see in the figure here, how it looks. Once we have got that 2D polygon, we convert it into an alpha shape. The alpha shape is telling me that, hey, okay, there's this polygon here, but a big an aircraft with a protected volume cannot enter this space anyway. So in a sense, all this space is kind of enclosed, and that's what the blue alpha shape is giving me for each polygon. Kind of, not necessarily a convex hull, but something convex hull or something of that sort, but kind of in that same essence. It's giving me a region over all the constructs that you cannot enter. Now I can process this, the data is processed, and now I can analyze it to understand what airspace is available. Let's spend a little time on this figure. Let's look at the figure on the right. Ignore the red lines for now. I'll come to it in a bit. The green box is the region we are looking at. This is San Francisco Bay Area. The pink here, the pink is the airspace which I cannot enter for UM traffic. So these are coming from departure arrival procedures in Oakland and SFO. These are temporary restrictions for Oakland Arena and AT&T Park at that point. Now it's also regulated. So the pink region gives you the airspace restricted. Of course, we use different color codes for different kinds of airspace. So pink is class BCD, controlled airspace and temporary flight restrictions. Black is terrain. Green and blue are the air arrival departure procedures. Then the red is the minimum vectoring altitudes. Of course, all of these restrictions are there, and now we can get empty airspace at every altitude. But the exact amount that I can get depends on what is my assumption on the operation of UAM. What scenario is it operating under? So that's where we came up with these 4 scenarios. The first scenario says that UAM can fly anywhere where they don't need to talk to air traffic control. That's why we call it ATC excluded, which means you can't enter any of the class BCD airspaces or the temporary restrictions. And the terrain, of course, is an obstacle anyway, right? So as you go higher in the air, more and more airspace gets eaten up by these controlled airspaces. The second one, we say that, okay, this is a scenario where every operation has its own airspace allocated to it. So you can be inside controlled airspace, you can talk to ATC, but you are given a region for you to operate under. So SUAs have their own region, UAM have the bigger ones have their own region. Aircraft are confined to their arrival departure procedures, but the rest of the class BCD is open under ATC, help. And then, of course, again, as you go higher at the bottom, there is no class BCD much, except for, there are no arrival departure procedures. They're very small on the ground level. And as you go higher, the departure and arrival procedures become bigger. The minimum vectoring altitude comes up and eats up the airspace. The next scenario is where we said, okay, here, the small and the big ones share the airspace. You can go above the minimum vectoring altitude, but you need to be in constant touch, especially if you are in proximity to the aircraft arrival departure procedures. So this is a little more flexible. So of course, more airspace opens up. The last one is even more flexible in the sense that it says anyone can operate anywhere, except if there is a conventional aircraft around, just stay away from that region, whichever one is active right now. So not the whole arrival departure procedure, but only part of it is active. And of course, that opens up a lot more airspace. This figure you see on the right is basically the small little one at 1,500 feet and just expand. Once we have the available airspace, now we can run different kinds of analysis. And that's where these stars and red lines come in. First kind of analysis which you can do is I can now overlay population density data on top of it. And this tells me that all the region that is covered by these constructs and I can't enter, which means the population in that region doesn't have access to UAM either. This gives you an idea of what population do you even impact given a certain scenario of operation in a region. Then this also tells you, oh, I want to put a vertiport in certain regions in the area. But this tells you that, as you can see, the red stars, some of the vertiports are not even accessible in this particular scenario. So this helps you in locating vertiports. Once you have the vertiports, the next question to ask is, oh, can you fly directly from vertiport to vertiport? So this is an example of a shortest path algorithm run to get point-to-point networks between the stars are the vertiports. You could be like, oh, maybe we should design a different kind of network where we should have more trunk and artery structure. You can again run that on these availability maps. You can also see, oh, you know what? Actually, a lot of these things here, there are too many aircraft interactions happening, but it would be nice if we could build a little air corridor through this for UAM and a little corridor through here. You can do analysis like that. Remember the helicopter routes I mentioned earlier that were used to design UAM routes in DFW? Well, here is a more formal way for Bay Area, right? Here is a more formal or mathematical way for network design. And of course, now you can modify these designs once you have them with subject matter experts and air traffic controller inputs and things like that. Any airspace study would require some basic for generating the flight plans and routes. And then you can test air traffic management strategies on them. Here is a tool that can now give you those candidate network designs. It could also inform, as I said earlier, the decision for placing vertiports. Which brings me to my final example, which is a study which I've been recently looking into. This is with Raja and Jane McFarlane at Lawrence Berkeley Lab, and Emmy, who is a new student at Berkeley now. And the idea here is we want to put vertiports based on the places where they will most benefit the public who wants to use it. So the question we're trying to address is, let's be as optimistic as possible, and what is the maximum traffic that will be benefited for a given use case? The use case we picked was about 300,000 cross-bay commute traffic trips in the Bay Area. We got this data from the mobility team at Lawrence Berkeley Lab, where they run these congestion simulations on supercomputers. Every origin destination pair, every trip has two alternatives. It could just either take the road route. We get the congested time from mobility. We get the uncongested time from Google Maps API. The other alternative is you go to the nearest vertiport and then fly from vertiport to the next vertiport near your destination, and then drive or take the road by any other means to get to your destination. A commuter will choose one of these based on how flexible they are to how much time needs to be saved. So it could be a rigid commuter who says, I'll only move to UAM if 50% of my travel time is saved. There could be a flexible commuter who says, oh, I will move if 25% of my time is saved. So to analyze this now, this demand shift, we first did k-means clustering on this data set, where I'm varying the k number. K number is basically the number of vertiports on east and west combined, right? So I have, let's say, one vertiport on east, one on west, then add another on each side, and let's look at the travel time trade-off. Let's add another one. We got to look at the new travel time trade-off. And as we do that, the number of people who would shift would ideally increase, because there are more and more vertiports to your home or your destination, and therefore you're spending more time traveling faster. So as I said, we estimate the optimal number of vertiports, where they could be placed, and the number of commuters benefited. There are two constraints, which I'll explain once I get to the graphs. Here is just a visualization of the east to west trip data. So east is origins, west is destinations in the Bay Area. We also had west to east, and we ran the analysis over the whole data set. The first graph is basically, I'm plotting my number of vertiports on east and west. And as I increase, for every combination, there is a number of commuters who are benefited by shifting them. And of course, this starts saturating as you get higher, meaning that let's say I have 30 vertiports on each side, adding a 31st doesn't really bring a lot more people onto the system. So there are two ways to now sift this data, right? One is, okay, let's say for a given combination, I have 100,000 people who would shift to UAM, but I have 10 vertiports on each side, which means on each vertiport, the average load is some passengers per hour, but that has a limit. So today, the best operations that happen is like 2 operations or something, about 120 takeoffs and landings at Atlanta airport or something like that, right? So if you take a similar number for the vertiport saying, oh, you're allowed about 125 takeoffs per hour, so 2 operations per minute, an operation every 30 seconds, we get to about handling 500 people per vertiport per hour. I can take this graph here, and I could divide each point by the total number of vertiports supporting it, which gives me the average capacity. And that's this blue graph. And I'm saying everywhere where it is above 500 passengers per hour per vertiport is infeasible. So all this region is infeasible. I can only get combinations in the other blue region. So this is my capacity constraint. There is a second constraint, as I said, adding a vertiport, if it doesn't bring enough people on board, then it's not worth adding because it's an infrastructure cost that I'm adding, but not for a big number. So I looked at, the BART statistics in the area, and a new BART station brings about 10,000 people on 9,000 people on board. And that's when a station is justified to kind of build. In that sense, I said, okay, let's say a vertiport is feasible to build if it can handle 1/5 of that load. So let's say it brings about 1,800 extra people onto the system over the day. Then that narrows down the feasible region to even more, or even smaller region, right? And out of that region, I now look at the combination, which gives me the maximum number of people. And here is what we find. For commuters who will shift with 25% time saving, we find a demand shift of about 50,000 people who would benefit from UM, no more than that. And that's under the case of assuming a 15-minute transfer, which is still, the Ubercopter in Manhattan takes about 10 to 20 minutes based on actual data. So this is what is possible today. If we could do a 5-minute transfer, of course, a lot more can move. For rigid commuters, at the 15-minute transfer, we had pretty much 0 people benefiting. So we looked at the next one, which was 10-minute transfer, and we had about 11,000 people benefiting, which is about 3% of our data. So meaning 3% of public is benefited. And you can get results like this. The other result which you can get from it is, of course, where the vertiports can be placed, the potential locations for these clustered data. Right? And this can inform the next study of saying, oh, okay, let's see where I want a vertiport in this region. This is a nice location, but around it is a feasible place to locate. To summarize, I can think of each example, as I kept telling through the presentation, in terms of the data science lifecycle. So for the airspace capacity study, we simulated our data. It was maintained as objects in the MATLAB simulator. The process is basically I'm clustering them by conflict size, and then I'm running a graph component analysis, and I could visualize the traffic, and I could produce capacity maps. The noise impact, again, simulated data, added population density and noise models to it. Again, flights as objects. I'm aggregating the data by the trajectory noise. Aggregating trajectories by their noise, producing the footprint maps for the region. And of course, I can generate these, intensity level maps and LN, the decibel exceeded level maps. Then for the third example, we got some real data from air traffic. We added simulation data. All that data is stored within flight matrices. And of course, there's a data warehouse, which has all the flight track data. From that, we are kind of clustering out, or actually selecting days, so we wanted to simulate traffic at different densities at DFW. So we selected days where the traffic was average over the year. And then we also selected days where it was very high. So that's off nominal days. Then our analysis was, predicting the TCAS alert rate and effect of altitude uncertainty on it. What we could produce to communicate what we learned are those encounter graphs that I showed you. Then the airspace availability was 2 examples. One was how airspace availability is done and how it can be applied. Again, the data we got was from 8 sources, 7 for the airspace constructs, then population density added to it. It's all maintained as 3D polygons. All the data is converted into geocoded 3D polygons. Then we process it to produce 2D shapes and do an alpha shape conversion. And then we can analyze the available airspace, the connectivity in the airspace, and things like that. And we communicate, of course, with those figures that you saw, and we can overlay a network. We could run a shortest path algorithm. We could show population accessibility and things like that. All of this is UAM airspace. We also started doing things about UAM airports, and that's the last example that you saw, where the data came from the mobility sim, Google Maps API, population density again, maintained as a matrix, processed with k-means clustering, analysis done was travel time analysis, and of course, I could produce the vertiport location maps and the demand graphs. And all of this is just the beginning, right? There are several other ideas that we have worked on, and even then we are still just beginning to scratch the surface. Which means that there are a lot of opportunities for everyone starting in the field. And the way I like to see the opportunities in the field is go back and think about the problems I pointed out earlier. all of those problems are also opportunities for you to make a dent in the field. And it doesn't just end there. There are a lot more questions that are new to the field. For example, today, all of conventional aviation is manned controllers, right? Manned air traffic controllers. Some of these operations in future are expected to be automated. Hopefully all of it can be automated for the UAM. But that doesn't mean you will change the manned air traffic control system. Very hard, because it's a system which has evolved and kind of got used to, and it's perfect. It's got a safety level much higher than road traffic. It's about 1 in a billion flight hours is the loss of life. But if you have automated controls, how do they interact? How do you make sure these different kind of human and automatic control interact with each other? So you can use artificial intelligence methods to understand that. Vertiport design, how do you minimize transfer delays? Because that is really crucial. As you saw, the transfer time is important. Where do you put the vertiports? Because of course there are noise concerns, there are accessibility concerns, how to move the passengers fast through them. How do you adhere to the zoning laws for the region? Some regions might have, okay, you can't put vertiports are great to be put in the water because they're away from all people, but then environmentally it's not right to do it. So there are things like that. How does land use change by putting a vertiport? That's another question. If I put a new vertiport, and Pawan knows a lot about this. If you put a vertiport in, let's say, Berkeley, suddenly either people could move away because there is a lot of noise, a lot of traffic, and the house prices might go up on the sides. Or people could converge, saying, hey, if I live close by, I can travel to work faster. That could cause a demographic shift, meaning people who work far could live closer to vertiports. People who work near homes or now working from home, I guess, can live wherever they like and mostly away from vertiports. And then, of course, there are so many stakeholders involved in the system. There are cities, counties, operators, air traffic controllers, the federal organizations, and each of them have their own restriction on what they can allow. And how do these different stakeholders resolve their conflicts to kind of come to a common ground? The network design tool that I showed you, well, it's not a tool yet, but the network design stuff that I showed you is an idea of an example that can be used as a negotiation tactic, where you say, hey guys, okay, you want the routes to be over water. If you put it here, this is how it helps the airspace side of it. This is how it helps the city side of it. Things like that. We have a lot of ideas, and people in general can have ideas for everything else once you can find the right data feeds. Here are some that I have discovered as part of my research. And of course, the traditional ones, Gonu listed them in the last presentation. I just summarize it here in 4 categories: airspace, geometry, flight plan, surveillance, and wind and weather. The even cooler and fun part are the non-traditional sources. So you should go and check it out. There are federal, county, and state data.gov sites which release a lot of this parcel data and things like that. Scour them. There is ArcGIS databases. There is land parcel geodata, which in some places is available for free, but most of it, I think you have to buy, unless you are, of course, an organization which has the resources and has access to it. But check it out. There's a lot available. There is a transit hub and network data, meaning where the hubs, where BART stations are, where bus stations are, and things like that. Land use and zoning data, rights of way data. This is another cool one, where the railroads and canals and transmission lines and pipelines are located. These are places where there are no people on them, right? So there are open spaces for you to fly. Wind is another important thing. So there's boundary layer wind models. Environmental researchers have them. We use something from Professor Tina Chow at Berkeley, where she had 100-meter grid data for wind, low altitude. Army uses a lot of wind models for chemical plume propagation in cities. So a lot of researchers have access to that. So that's another data. I just wanted to leave you with this list to kind of get you started with data science for urban air mobility. All I would like to say at the end is, explore and innovate. Thank you for attending this whole, not just this talk, but the whole seminar series this semester. It was a first attempt. And we are learning as we go too. Actually, in that picture, actually, you can also see data capture, maintenance, and processing happening at the same time. But yeah, any questions, comments, suggestions, welcome. Thank you again.
Hey,
thanks so much, Vish.
This is Jeremy. I just have a quick comment, or maybe a question too. If I understand correctly, you were modeling vertiport capacity to be equivalent to Atlanta. Is that correct?
No, Atlanta was an example. What we modeled it is, we said, if I allow 2 takeoff landings per minute, each aircraft, let's say, can carry 4 people, excluding the pilot. That's about 120 takeoffs and landings combined over an hour, right? So
Yeah,
that means about 480, 500 people over the hour. That's how we got. Atlanta was an example to give a reference for what happens in the airspace today.
No, I understand that, but I would say that, you know, using the rate of takeoffs at the most busy airport in the world might be a little bit optimistic for vertiports, but, you know.
Very good point, Jeremy.
And one other comment too is that, you know, when major airports are close to each other and interacting in some type of metroplex environment, that further constrains the capacity because they're sharing resources. And so now when you show vertiports and you have 30 of them in the Bay Area and they're all quote unquote able to handle, you know, 2 operations per minute for departures, that just might be a little bit optimistic.
You're totally right about that. And that's why the question that I asked was not, oh, how many people can fly? The question I was trying to answer was, hey, I want to convince a city or a county to invest in UAM. I have to tell them, you know, UAM will shift 3% of the traffic. Even by being all that optimistic, if I can't move 3%, then of course, with all the constraints, I can't even move 1%. And that's the answer I was trying to address. And that's why there were all these optimistic assumptions, which basically is saying, oh, I cannot move no matter what I do more than 10,000 people of this data set. Does that explain what I'm trying to say?
Okay, so I guess that is, so I guess in the context of if you're trying to provide an upper bound, but you know, some of the risk is if you communicate these expectations and you get the hype up, and then you know you can go down the other side of the hype curve. So that was
yes.
But good talk. Thank you.
So Jeremy, just a quick comment. I think what Vishwa was trying to do here is not to model after an airport like Atlanta, but basically the calculations that he did based on his assumptions indicated that the rates that he got would be similar to something like Atlanta, which is pretty challenging.
I understand that, but I guess, I mean, it's just a guess or an assumption of what the rates at a vertiport would be. Is that correct? We have no knowledge or like real confidence in what those would be.
So you're right, Jeremy. It will be much lower than that. I want to move to the next question quickly. There is a question here in the comments. Was any thought given to exploiting existing major highway corridors for UAM traffic? Yes, there is a study we did in my earlier research by the student called Zilong Lu, who actually generated highways based on the existing road highway corridors in the sky. We didn't simulate as much traffic, but that data is still available. So we can always take this offline and talk about it. Brian, I guess that's the person who asked this question. Jeff Sharp has a comment. Aircraft carrier operations could be better comparison than ATL. Oh, then Atlanta. Okay, there you go. Here's a comment on.
Yeah, I got that you were trying to model an absolute best case scenario, but if somebody did want to model something that was a little bit more realistic operations, either the light helicopter carriers or aircraft carriers could be an interesting comparison.
Great, thank you. Yeah, I like that idea. Let's talk about it. Okay, any other questions?
Hi, Vish, this is Sagada. Hey, I was just wondering, there is another kind of air transport coming up. It's like a personal air vehicle. This man called Richard Browning in England, I think, he has a suit where you can fly. It's not a, so basically that kind of traffic, if you think that is coming to near future, have you ever thought of that taking into account this kind of stuff?
I actually haven't, and it would be a good thing to consider. Thank you. Yeah, I like that.
You're welcome. Great talk.
Thank you. So I'm here as maybe another 5-10 minutes if people have questions. And Pawan, if you want to wrap up, go ahead.
So as we wrap up, thanks, Vish. If anyone has more questions for Vish, as he said, he'll stay on the line. We wanted to end this talk in the semester with a few words from Dr. David Bell of USRA and NAMS. Dr. Bell, if you can step in and say a few words, that would be great. Okay. David may not be.
Maybe David's not on the line.
David,
Yeah,
I'm sorry, Pavan, 1 second. I'm just checking to see if his internet connection.
No problem.
Can you guys hear me?
Oh, hi, David.
There you are.
I did.
Okay.
Yep. Go ahead. The mic's yours.
Hi.
David, we're unable to hear you.
How about now?
It's a little better.
Let me try.
Yeah,
One last
that's
thing.
better.
I think I can try. How's that?
Yeah, that's good.
Okay. I just wanted to thanks Vish for a very nice talk. I wanted to thank the organizing committee for pulling this all together over the course of the seminar series, and Raja and Mark for organizing this joint Berkeley USRA-NASA event. Also, and I know this is ending for the students, we are going to try to continue the seminar series. And so we will, if we can get speakers who are willing to do the webinar only format going forward, we will do that. I know a lot of the aviation industry is going through a really rough time right now. The volume through the has dropped significantly because of all the shelter-in-place orders. But we're working to get some of the industry and government speakers ongoing as well. But thank you again to the organizing committee and the Berkeley faculty for helping organize this thing.
Thanks, David. We do appreciate all the work that was done with this seminar this semester, and we hope to move forward strongly in the future. Sam, if you can just mention a final bit again to the students who may not have heard regarding the end of semester assignment. After that, we'll close out the seminar for the semester. Thanks.
Yep. Great, thanks, Pawan. So just to remind the students enrolled in this seminar course as a 198 or 298, you would have to submit a one-page write-up just with the key learnings that you've acquired through the seminars. Any 4 seminars, just mention them. The recordings are available on the USRA website. I've put that in the seminar, in the assignment description. So if you have any issues, just email me. My email's in the B courses description. Thank you.
Okay, thank you, everyone. Thanks, Vishwa, again for ending the seminar and ending the semester with a bang. And we look forward to having everyone join for future versions of the seminar series. Thanks so much.
I just left my email in the chat in case people have questions. Just feel free to hit me up. Thank you.
Thanks. Bye.